All right, today we're cracking open what I like to call the hacker's toolkit. We're going to uncover some incredibly powerful, super efficient techniques that work right at the machine level, the very foundation of how computers think. So, what if I told you there's this secret language for numbers? A way to see them that could literally let you solve some interview problems, maybe even 10 times faster than you normally would. Well, that's exactly the power we're going to unlock today with bit manipulation.
So, what is bit manipulation, really? Honestly, the best way to think about it is this. Forget numbers for a second. Instead, picture a long row of light switches. Each switch is a bit. It's either on, which is a 1, or it's off, which is a 0. We're just going to learn how to flip them, group them, and shift them around like pros.
Here's the game plan. We'll kick things off with the absolute must-knows, our core identity toolkit. Then we'll see how to actually use those skills for counting and messing with individual bits. After that, we'll get into the magic of the XOR operator, peek at some really cool advanced stuff, and then wrap it all up with how to nail this in your next coding interview. First up, the core identity toolkit. Seriously, think of these as your fundamental moves. These are the ones you just have to know. They're non-negotiable skills you'll want in your back pocket. Okay, check this out. This is probably one of the most famous tricks in the book, x and x minus 1. Let's just walk through it. Take the number 12. In binary, that's 1100. Now subtract 1. You get 11, which is 1011. See what happened there? That rightmost 1 flipped to a 0, and all the zeros to its right flip to 1s. So when you perform a bitwise AND between them, boom, the lowest set bit just vanishes. We're left with 1000, which is 8.
And that's not some weird one-off thing. This trick works every single time. It always clears the lowest set bit. It's a rock-solid pattern you can count on whenever you need to switch off that rightmost 1.
Okay, cool trick, but why do you care? Well, this little pattern is your secret weapon for a couple of classic problems. You want to know if a number is a power of 2? Easy. Powers of 2 only have one bit switched on, so if x and x minus 1 equals 0, you've got yourself a power of 2. Plus, this is the engine for a crazy efficient way to count all the set bits in a number. We'll get to that in just a minute.
All right, the second core move you gotta know is how to isolate that lowest set bit. The magic pattern for this is x and negative x. It's a clever use of how computers handle negative numbers, something called 2's complement, to create a brand new number where only that one single rightmost light switch from your original number is still on. Okay, we've got our basic toolkit. Now let's actually put it to work. We're going to see how these simple moves let us tackle more interesting problems, like counting up all the bits, or even getting in there and changing them one by one. All right, this is Kernighan's algorithm, and it is just so elegant for counting bits. It's super simple. You set a counter to 0. Then you just keep looping as long as your number isn't 0. And inside that loop, you just use our trick, x equals x and x minus 1. Each time you do that, you knock out the lowest bit, and you add 1 to your counter. You just do that over and over until all the lights are out. And this is why that algorithm is so stinking smart. Its speed, what we call OK, isn't about how big the number is. It's about how many bits are turned on. So for a number like 15, which is 1111, yeah, it takes 4 steps. But for 16, which is 10000, just 1 step. It's a total game changer for numbers that don't have a lot of ones.
And here it is, your go-to cheat sheet for getting your hands on one specific bit. If you want to know what the ith bit is, you just shift it all the way to the right and AND it with 1. To turn it on, you use OR with a special number called a mask. To turn it off, you use AND with an inverted mask. And to just flip it, that's where XOR comes in. These 4 moves are the building blocks for pretty much any bit-level work you're going to do.
Okay, now it's time to talk about one of my absolute favorite operators, XOR. There's this magical quality to it, a power of cancellation that lets you solve some really tricky-sounding problems in the most beautiful, simple ways. All right, let's play a game. Classic interview question. I give you a big list of numbers. Every single number in there shows up twice, except for 1. How are you going to find that lone wolf and do it fast? The entire solution hinges on these 3 simple facts about XOR. First, you XOR any number with itself and you get 0. They just cancel out. Second, you XOR any number with 0 and you just get the number back, unchanged. And finally, the order you do it in doesn't matter at all. With just these 3 rules, we've got everything we need. So look at our input array here. If we XOR all of these numbers together, remember, the order doesn't matter, so we can kind of mentally group them. We've got a 4, XOR 4, which is going to become 0. And we've got a 1 XOR 1, which is also going to become 0. And what's left? The 4's canceled out, the 1's canceled out, so you're left with 0 XOR'd with 0 XOR'd with 5. And since anything XOR'd with 0 is just itself, the answer is 5. Just like that. The pairs literally disappear, and the unique number is all that's left. I mean, how cool is that?
So, we've hit the main patterns you'll see in interviews, but this stuff goes so much deeper. Just to give you a taste of what else is out there, let's take a quick look at a more advanced pattern.
For instance, ever heard of gray codes? In normal binary counting, when you go from 2 to 3, you actually have to flip 2 bits. But with a gray code, as you count up, only one single bit changes at a time. This is a super useful property for things like hardware design because it helps prevent errors when things are changing states. Okay, let's pull all this together and talk about your interview playbook. Because it's not enough to just know the tricks. You have to know how to talk about them in a way that shows you really get it. So step 1 of the playbook is to just master this core toolkit. Seriously, if you remember nothing else, remember these 5 patterns. Know how to isolate the lowest bit, how to clear it, and how to use that to check for powers of 2. Know Kernighan's algorithm for counting bits, and of course remember the XOR trick. These are your bread and butter. And here's step 2, the pro move. This is the kind of thing that makes interviewers sit up and take notice. Before you even write a line of code, just state your assumptions. Hey, are we assuming 32-bit integers here? Or how should this handle a 0? What about negative numbers? Thinking about those edge cases up front, that shows you're not just a coder, you're a serious engineer. And, just to put it all in perspective, it's pretty wild to see where all these ideas came from. This isn't new stuff. It all started way back in the 1850s with George Boole's algebra. Then the genius Claude Shannon connected it all to electrical circuits in the 30s. Patterns like the gray code were patented in the 50s. The things we've been talking about are literally the bedrock of all modern computing. So there you have it. We've gone through the theory, the patterns, the whole playbook. The only thing left to do now is, well, do it. Get your hands dirty. So I'll just leave you with this one question. You've got the toolkit now. Which LeetCode problem are you going to crush first?